Welcome back to Bargaining in War. This lecture is on the ultimatum game for crisis bargaining. In past lectures, we've explored whether there exist settlements that both parties prefer to war. What we haven't yet done is explore which settlement the states will actually choose, nor have we used any sort of game theoretical modeling to help us answer that question. This is going to be a problem for us in the long term. Crisis bargaining theorists care a lot about how changing the inputs of a strategic scenario affect its outputs. For example, how does increasing one state's power or decreasing the cost of war affect the probability of war versus peace? At its core, that's a question of comparative statics. But to take a comparative static, the first step is always to solve for the equilibrium of a game. Yet, we cannot solve for the equilibrium of a game until we have a game in the first place. And that's what the ultimatum game is going to do for us. There are two reasons why we're studying the ultimatum game and not some sort of other bargaining protocol. First, if you take a random article from the crisis bargaining literature, more likely than not, the author is going to be using the ultimatum game to explore the phenomenon of interest. Thus, if we are going to look at any one bargaining protocol, it must be the ultimatum game. The second is more theoretically justified. I don't want to go too far into this because it is getting pretty deep into the literature, but imagine that you were involved in a crisis bargaining scenario and you got to choose how to bargain over the particular good at stake. Well, we have some results in the literature that show that it would be optimal for you to choose to make an ultimatum. In other words, say to your opponent, I am going to take this much, you can take the remainder, and if you don't like that, then you must fight me. You can think about how that might be theoretically justified by if you have control of the strip of territory already, the way that you might go about negotiating with your opponent is to retreat to a particular point and then tell your opponent, this is the new border. If you don't like it, let's fight a war. And now that I've previewed the substantive idea behind an ultimatum game, let's now formalize that down into a model and solve for its equilibrium. The ultimatum game is just a two-step process. First, State A will make a demand. And like normal, you can think about this as a percentage of the good that is going to A. So X is a quantity that is between 0 and 1. B observes A's decision and then accepts or rejects it. And that's the end of the game. Very simple, very straightforward. The payoffs are going to follow from what we've learned about previously. We're not changing anything there. So if B accepts, A's share of the division is X, so that's its payoff. And B gets the remainder, so B's payoff is going to be 1 minus X. If B rejects, we get our normal war payoffs. So A will receive P minus CA, and B will receive 1 minus P minus CB. How do we solve this? Well, just like any sort of complete information game that has multiple steps, if we can start at the bottom, that's where we should start. We should try to apply backward induction as far as we can. So for here, that means looking at B's accept and reject decision, and to figure out when B prefers to accept versus when it prefers to reject. Let's start with the accept case. B earns 1 minus X if it agrees to a deal, and it gets 1 minus P minus CB if it rejects. So solving for X, which is ultimately what A is going to be demanding, if X is less than P plus CB, then that implies that B accepts. It must accept. Well, by analogous argument, if X is greater than P plus CB, now A is demanding too much, and so B rejects. And likewise, when X is exactly equal to P plus CB, then we have B being indifferent. For the purposes of this lecture, let's imagine that B accepts with certainty when it's indifferent. In the next lecture, we'll look at this a little bit more in depth and show that in fact there are no other equilibria where B is going to be doing anything else. So in any equilibrium, it must be the case that B is accepting when indifferent. And again, we'll talk more about that later on in the next lecture. For now, just go with this. Let's imagine that this is B's decision and how it's going to respond to any given demand from A. Well, once we're armed with that knowledge through backward induction, we just go up to A's demand and figure out which demand is going to optimize A's payoff. And that will be the demand that A ultimately implements. Well, let's think about this as a number line. We're varying the value of x, and there's a single cut point of P plus CB. If x is larger than that amount, then we have B reject. And if x is less than or equal to that amount, we have B accept. So all I am doing is plotting this information on a number line. Now let's use this visualization to figure out what is A's optimal demand. Well, first, let's note that any demand in this region is going to be rejected. It doesn't matter which. Every one of those is rejected. And A gets the same payoff for that scenario, which is P minus CA. It gets its war payoff from up here. Okay? Well, then the other thing that we need to look at is this range of offers that B is going to accept. And once we figure out which of those demands that A can make that maximizes its utility within this accept region, we need to then compare the utility for making that demand to making a demand that B would reject, thereby giving A a payoff of P minus CA, and see which of those two options is better. Well, it turns out there's going to only be a single demand that could possibly be optimal if A wants to get B to accept. Let's think about some demand that is lower than the cut point. Say right here. Imagine we have X as the demand. Well, B accepts, and so A's utility for that is just X. But compare that to some demand slightly larger, by an epsilon quantity more. This is still within the region that B accepts, so A's utility is still going to be whatever it demanded. The difference, of course, is that now it's getting additional epsilon because it's demanding slightly more. So there is no reason why you would only demand X when you could demand X plus epsilon. But that's not going to be optimal either, because you could always demand epsilon more and still get B to accept and get more for yourself. But that logic applies further and further on, further and further and further on, until you can't get any further. Namely, if A is going to demand P plus CB, if it tries demanding anything else, extra, B is going to switch from accepting to rejecting. So none of these demands down here can possibly be optimal for A, because demanding this quantity is going to be better for it. There's always some slightly larger demand that A is going to be better off by making. So what that means is that the question really just boils down to two options. Does A want to demand P plus CB and keep P plus CB for itself? Or does it want to make any sort of unacceptable demand, have B reject it, and then get its war payoff of P minus CA? Well, if that's the case, all we need to do is make a simple calculation of whether A prefers the amount where it's getting P plus CB or it gets P minus CA. And very clearly, we have an answer. Obviously, P plus CB is better than P minus CA. In fact, if you just rearrange this, the end of the proof is going to look pretty similar to what we have seen previously. So you'll see that A prefers making that optimal demand that is going to be acceptable of P plus CB, as long as CA plus CB is greater than 0. In other words, as long as war is inefficient. It is not a coincidence that this is matching the previous ends of proofs that we have seen. If A is going to fight a war, that is costly. It doesn't benefit anyone. And by being the state that is able to make the proposal, A can make B just indifferent between accepting and rejecting, which means it gets to save its costs for war by not having to fight and extract B's cost of war. A makes out like a bandit, so there is no way that A is going to intentionally sabotage negotiations. If this isn't clear, let's just do a single graph of what's going on with A's payoff, and that might clarify what's going on in A's decision. So here on our x-axis, we actually have X, the demand being made, and on our y-axis, we have A's utility as a function of X. And we have this critical cut point of P plus CB. So what we see is that anything to the left of P plus CB is going to be accepted, and A's utility is just equal to the size of the demand. So that increases linearly. And if it makes that demand at the cut point, it receives a value of P plus CB. Meanwhile, if it chooses anything greater than P plus CB, then B rejects. And so A's utility is going to be a flat value of P minus CA. So again, you'll notice here, because we have assumed that B is going to accept when indifferent right here, that B is giving A this quantity up here when it is having the demand of P plus CB, and we're not having this rejection payoff down here instead. Well, if you're A, your decision process really is just looking at this figure and deciding what is the X associated with my highest utility. And it doesn't take very long for A to realize that that demand that's best for it is P plus CB. End of story. Done. So to recap, in the ultimatum game, A demands X equal to P plus CB. And what does B do? Well, B accepts X less than or equal to P plus CB and rejects X greater than P plus CB. This is our subgame perfect equilibrium of the ultimatum game. That's it. That's all there is to it. In the next lecture, we'll deconstruct this assumption about B accepting when indifferent and see why, in fact, this equilibrium that we have described for the ultimatum game right here is, in fact, the only equilibrium. Hope you enjoyed this and hope to see you next time. Take care.